specifically. We have with us Gopal Hari Vijay. Please come on the stage. He is our next speaker. He holds a master's degree in VLSI Design from National Institute of Technology, Trichy, graduating in 2001. He has worked on various chip designs ranging from automotive to cloud servers for companies such as Motorola, Texas Instruments, and Intel for over 16 years. During his earlier employments with chip design companies, he contributed to 7 international journals related to formal verification at the RTL level and physical design. At Zoho, he has been working for 6+ years now on video AI accelerators, with his work being recognized by both Intel and AMD. Welcome, Raja, and all the best for your session.
Thank you, thank you. Thank you for a generous introduction. We used to get servers with 1 kilowatt hour, which consumes 1 kilowatt hour. So we could actually build 10 servers in a rack, which is a 10 kilowatt rack. Nowadays, we are getting servers with more than 2 kilowatt per hour, right? Which consumes more power. Not only that, in order to cool that server, we need water, right? Because the AC works on water. And it takes approximately 1 gallon water to cool one server if it runs 24 hours, right? Which is typically, if you combine that water consumption for a week or so, it actually takes 8 people's, water. Basically, the water consumption is equivalent to 8 people's water consumption, right, in a day, because it's a clean water that is needed, and the air, correct? And we get electricity from the solar power, correct? Or we know that many data center companies are started building nuclear reactors for getting the power. But who is going to give air and water? From where, which planet is going to give us air and water? That's a precise question that needs to be answered, right? And our organizers and generous sponsors have set the theme of this conference as sustainable innovation. So sustainable innovation has 3 elements basically. One is environmental responsibility. Second one is economic viability. Third one is social equity. Right? Environmental responsibility is using all the natural resources in a way that the future generations can also survive and live. And with respect to economic viability, obviously it needs to go. AI needs to be accessed by all of us. Right? The third one, the social equity. The power consumption of certain data centers today is equivalent to the power consumption of certain countries. So all the data is out in the internet. I just did a small comparison to use certain analogy here. So this conference theme has actually put in a social message for all of us, because all the AI and the silicon that actually runs on the silicon, and that being a semiconductor professionals, we design silicon. So they put a strong message the social message for us to think, act, deliver accordingly, and that's why this conference is. So I invite you to give them a loudest, heartfelt applause for setting up this conference and thinking in the direction. Thank you. Zogo. For those of who don't know about Zogo, Zogo is the largest Indian multinational software product company who can compete against Microsoft across all the product ranges. In fact, this is the only company who can compete across Microsoft, across all the product ranges. And our customers also pay for maintaining their Microsoft stack. So we have 100 million users, paying users, more than 2.5 lakh businesses, and the revenue of more than $2 billion. Right? And this is our first presence in such a esteemed semiconductor forum. Zogo is venturing into AI semiconductors. Okay. So, the previous sessions, IBM has covered most of the thoughts, approaches related to AI inferencing and how do we save power and etc. But I'll try to give my perspective on how we actually did this 90-minute journey, right? Okay, disclaimer. The content of this session is completely learning purpose only, and because we focus on open source this time rather than the proprietary data set, proprietary designs. And I'm sharing only the insight that has been learned, not the information, because most of the technical sessions have covered all of those. I do not want to repeat and bore you. And sometimes the results may vary based on specifications and configurations, right? Okay, this is a long title, but I'll be focusing on the inference side of the AI, and we'll be focusing on open source. How do we use open source for a resource constrained systems? Resource constraint means in two aspects, whether you have less capital to develop such an inference chip, as well as we may not be able to have supply the power or with respect to the environmental responsibility, right? So from that aspect, I'm covering it. Basically, I go in this order. Whether it is feasible to design such a chip, right? Second one is, if it is feasible and it is really sustainable. Third one is whether it is economically viable. And affordability. Viability is in terms of making the chip design successful. Affordability is with respect to the cost, and scalability can make all of them use. Can we make them useful for all of us, right? So that's what the aligned to the theme of this conference: environmental responsibility, economic viability, and social equity. Okay. What do I mean by open source? Open source is free to use with or without modifications. Most of the content that you find, the code that I refer, the tools that I refer, is available on the internet. There are a lot of experts and professionals who has actually put in a lot more effort in detailing it with YouTube videos, blogs, and more articles, right? And so we can refer to that. Open source is not only free to use, but also we can distribute, redistribute to somebody else also. So it is completely license free. Okay. Open source in the context of startups. Obviously, it is going to reduce the cost, not only from the development perspective, but also from the making business perspective. Because if it is open source, then it is basically follow some kind of standards. So we can actually merge our chip into the ecosystem very easily, right? And community develops it. Community is not the people of, it's not only the people of professionals, but also it, it, it is, they are passionate to do some kind of, service other than, being professional, right? So they'll put lot more heart and soul, or head and heart, to develop it. And collaboration, this obviously enables a lot of collaboration between companies, between academics, colleges, and community and corporations, because you don't need a lengthy legal compliance, NDA and stuff like that. Basically, it helps us to achieve compliance because it's going to be the open source, right? From the enterprise perspective, so if it is a cash-rich company, right, how does it going to help for them? So most of the professionals and experts in the same conference have shared about adopting AI and ML models for chip design process. When they shared their strategy, they also shared an important point that they do not have enough data set. Correct? So this open source, we can actually employ it in our own design, in our own corporation, and generate enough data set so that we can have our own AI models for the chip design purpose. Development perspective. So basically, we can actually try out new algorithms, because EDA comes with proprietary licenses. We get a lot of options to drive that proprietary tools, and it is more efficient, productive, cost effective, and all of those things are there. But it can also help us find out new algorithms which are specific to our own design, right? EDAs generally applies to large mass. Sometimes they may miss out few points locally for our benefit, right? So for the individual design. So we can actually cover that. With respect to the differentiation, enterprise can come up with product ranges right from in all price ranges, from the cost effective till the premium range, and deployment is the same. From the professional standpoint, yeah, open source helps us to explore new ideas, experiment, and eventually experience and gain experience and develop expertise, because more than 1/3 of the semiconductor professionals, the experts who had driven this industry some 30, 40 years back, they are all retiring. So young professionals like you and me have an opportunity to use open source and then develop more skill set. Okay, I know you might have heard a lot about AI and every presentation. I'll just try to give my own perspective, my own understanding about AI. So we might have come across these possibilities, these benefits, right? One is achieve more with fewer resources, unlock new possibilities, make experiences personal. Unlock new possibilities means that enables us to do new stuff which we couldn't do it before. Make experiences personal means the Apple intelligence, the mobile intelligence is all more personal to us, and scaling knowledge effortlessly, and inclusive and empowering for everyone. So AI has improved the accessibility, right? I'll focus on two things, right? One is achieve more with fewer resources. Basically, in let's say, if you take any cloud companies who offer AI, proprietary AI, we can actually generate 900 million tokens per year that cost around $30K. Fine. What is this 900 million tokens, right? So if I give a perspective of what is equivalent to 900 million tokens, we are also developing an operating system which is tailored for Zogo workloads. That's called the Surya OS. I'm responsible for that as well. It's based on Linux. With that experience, I can say that with 900 million tokens, we can create almost 250 operating systems from scratch per year. Because The Linux code base is approximately 30 to 33 million lines of code. Right? So that's the power that AI gives us. And most of the experts in the same conference yesterday and going to share, has already shared, and the experts who are going to talk about it have given a lot of strategy that how do we make enough sense out of LLMs for chip design, for all the other kind of work, right? So if we follow all those strategy, this becomes really viable for us to create more than 250 operating system variants from scratch, right? At the cost of $30K. Think about the employment, right? With respect to the employment, $30K is approximately 4 juniors and 1 senior. That's the cost. But Linux has been developed, approximately more than 25,000 engineers have contributed so far, and every year approximately 6,000 to 8,000 people are committing to the repository, and those experts are from different companies. So you can think of 250 variants of operating system with the cost of 4 engineers, and so this is the perspective that is coming in, and scaling knowledge effortlessly. So technology, resources, capital, and labor, all the previous 4 generations of industrial revolutions, or 4 or 5 generations of industrial revolutions, had played a multiplying factor. When we put more technology, when we put more resources, and technology means machines, cars, automation, and all that stuff. If we put more capital, more labor, correct? The AI is actually giving the exponential benefit. Let's see how. On both sides, right? On the positive side and the negative side. I'll take the negative side first. Suppose an employee leaves an organization, right? He or she takes away all the relationship that is built within the organization with the customers, with the teammates, etc., right? But whatever they have delivered, like RTL design, verification plan, PD, all of those things are checked into the repository. So whatever they have contributed to the organization is there already. But when an employee leaves, right, he or she takes away the other set of relationship, correct? So if somebody joins new, right, and who is going to take care of that responsibility, will miss a bigger picture, correct? That's true till today. But it's not going to be true from now on. Think about it. Let's have the new employee gets access to the code repositories, the plans, the documentation, whatever they have created it, right? And some part of the tickets they have access to, but not all the emails, not all the chats. And if an organization, develops an AI to understand all of it, they can retain most of it. So we may need a new metric to calculate the retention, correct? And the company is going to benefit. They are not, because they are accumulating more and more knowledge. With respect to, on the positive side, I myself do not remember what I have written 4 months ago, a year ago, or what I have done while checking it, while turning in the code and stuff, right? And if it becomes my assistant, it's going to help. So it's going to exponentially increase the power of labor. Okay, what is AI? Okay, from the another perspective, because I'm just trying to build, I'm covering the whole area from idea to implementation. So I'm trying to stick more fundamental than being technical, because IBM has already covered most of it in their previous presentations, right? With respect to writing a program, right? Specifications, once we get a specification from the customer, we try to identify how do we write programs and things like that, software architecture. So we try to convert the specifications to instructions and then try to convert that into a program. That's what the programmer does. In the AI context, right? In AI, we actually feed, rather than coming up with the specification, we actually feed the knowledge and then guide the process and get the model. For example, I take this analogy that we have a set of syllabus to be covered in the college or at the workplace, and we have the set of documents and stuff, and then we ask the mentor asks the mentee to read and come up with answers, results, and then they try to guide. Once they find they are qualified enough, the model is released. Basically, the context is learned there. Because whatever the information that is being given, it is information, not the insight. What the mentor trains the mentee is building their context, building their knowledge, right? So basically, we try to feed the knowledge and then guide the process and get the model out. And there is a difference between specification and knowledge, correct? Specification is more like a data sheet. You can refer the data sheet and find it out, but knowledge you cannot, right? Because that's where it tells us, it helps us to find out where we can apply it, right? How? So how many of us have WhatsApp display picture? Okay, good. At least only one hand, right? Okay, so I use more analogies here. AI is nothing but dp square. So dimensionality, and the p is pattern, and the p is predict. So you can always remember it as dp square. Okay, with respect to dimensionality, right? Some of the tutorials have mentioned that humans can recognize only 3Ds, 3 dimensions, right? Length, width, and depth. Correct? Let's see. I'm trying to cover some of the context here. So on my right, it is all the natural elements. On the left, it is all our senses. Okay. So Earth is actually represented here as one dimension, because when we stand on the Earth, correct, it is one point. I can only mention a point. Or if I walk, I can actually draw it as a line or curve. It is basically one dimension. And with respect to the smell sense, correct? So this is the only sense that actually recognized by the brain. There is no intermediary. Okay. And 2, the water. Correct? It's a 2-dimensional. When you put a water, it is actually spreads. This is the length and width. And that's where our taste buds are actually the rectangle. This is a 2-dimensional. Correct? And we can sense the taste only through water, the fluid nature. That's how the nature has set it up. And fire. Fire actually, heat is a byproduct. It is not a natural quality, things of fire. It's a light that they are referring to. And our eyes has cones and rods that actually senses the light. And 4th is the wind. And the wind is actually, we can feel wind only through the touch sensation, right? Because you need some time to feel that touch, right? So it is 3D space with time. Okay, and the last element is sound. Sound actually can help us realize multiple spaces. How? If you close your eyes, right, and you hear a sound, you can, from the source of the sound, you can actually identify the distance, direction, and the 3D space that you can come up with. And sound is the energy we can actually build so many things, right? It helps us, connecting multiple dimensions. Okay, this is one side of spectrum and this is another side of spectrum, and all these things can be connected via mathematics. That is why mathematics is called as the language of God. Okay, what is AI, correct? So first part we have covered dimensionality. So we can actually increase our dimensionality, the perception of dimensionality, and we can build upon, right? After building a dimensionality, we need to find out the patterns, right? How do we find the patterns? Okay, what is the difference between the left and the right, correct? So in the previous session, they talked about the MNIST. How many of you guys know the MNIST? Good. And the right hand side fashion MNIST? Okay, good. Okay. When you look at it as the shades of the color, right? It is white, gray, and black. So the shades are between white and the black, correct? And what are we trying to find out? Right? How does this knowledge is being gained, correct, from this diagram? Because when you compare the pixel values, it is between black and white, right? And that is what it is called context. That is being. If I give the neural network to recognize these digits, and I cannot use the same neural network to recognize this, I need to retrain. Okay, let's see how. Okay, and this is the number of pixels that we have. I mean, this is the picture that you might have seen from the previous presentation. It's a 28 pixels wide and length enough, and we actually convert these pixels from 1 to 784. We call each one as dimensions. Each one pixel color as dimensions, and the neural network recognizes it's a 8, right? Okay, I'm trying to find. So we have seen the dimensionalities. Now we are trying to see the patterns, right? How do we recognize the patterns? How do we get this context into the neural network, right? I'm just trying to be as fundamental as possible. You might have seen this filter, right? This is a convolution. You can call it as a filter, not convolution as of now. It is a filter. When the filter has a specific value and apply it on the picture, you will get, this is a blurred picture. This one is the blurred one because I'm trying to average the pixel colors and then assigning it, correct? And this one, I'm trying to find out the gradients. So basically, when I apply the filter with 0 values in the middle and the positive and the negative values at the top and bottom, it is trying to find out the horizontal gradients. Gradient is change. How does it change, right? And you find that in the spaces, it is not at all, there is no change because it is almost similar. But in this side, you will find a change. And here, this is a change because this building, you can find it out, and this is not a change according to this filter. So we try to find out gradients across all possible angles. How do we decide about the gradients? That actually comes from the data set. So this one is horizontal, this one is vertical, correct? And just explain the previous process in detail. So this is the filter that we are trying, this is the image, and this is the filter, and we try to apply it on the image, and then we get this value, correct? Likewise, if we do, for the entire image, we actually build the feature map. What is feature? Let's say how many 45-degree angled lines are there, how many 90-degree lines are there, something of that sort, right? That feature map is basically defined by the filters that we run on. Okay, and this is actually the illustration. This is not actually the true picture. We cannot see as clearly as this within the neural network. But as I said in the beginning of the presentation, all these black and white refers the colors of the images, and we are trying to learn the context from the filter. So first we try to find out how many lines are there, and then we try to construct eyes out of it, correct? And for cars, we will try to find out the tires, right? And for elephants, this is the structure. For chairs, this is the structure. basically using the same bone, same structure of the neural network. If we give the data set with respect to faces, cars, and elephants and stuff, we can actually train the neural network, and that weights applies only to that data set, right? So basically, this is how we build the context of this. So CNN, the convolutional neural network, tries to group. So if you have find out IKEA or any other toys, right? They'll self-assembly, do-it-yourself toys, right? They'll actually give the set of components, and then we open it, and then we try to assemble it, and then make sure it looks like the same, right? Similarly, CNN feature maps are like a set of components that we can build something out of it, right? So the filters are nothing but the predefined weights, and the convolution is actually the process. And filters have the DSP filters have the static weights, as we have seen in the previous slide, and the filter values are actually learned from the data set, as I have shown it in the. So the filter values of this side data set and this side data set is going to be different, but it can be in the same neural network backbone. Okay. And we extract only the features in the filters, but in convolution we try to map the data. Okay, rather than so how many straight lines, how many slanting lines, how many curves are there, etc. So fundamentally, the context tower is nothing but the pixel values that's detected, and the L2 edges. The first convolution layer actually detects the L2 edge. The layer 2 actually detects the edges, and L3 layer actually combines all the edges together, like we see the how we construct a toy. And fourth one is about the features identified, and fifth one is the dense layer, which is a decision making layer, where how many to recognize one or a car, do we have all parts of it or some parts of it? If there is some parts of it, whether it is actually a car or something else. So that decision will be made in the dense layer, because all these layers pass some kind of templates from the first layer to the next layer, right? And that template will be compared. When you do a dot product, it is actually a kind of trying to match a pattern and see whether those patterns are there. So we have seen the dimensionality, we've seen the patterns, and then we are trying to predict, right? Which that prediction layer is actually the dense layer. And we have some kind of mathematical operations and all of those. It's not as simple as I say, but this is the fundamental to all of the neural network. Okay, from the architecture design, now we have seen the idea of how do we build inference chip, inference chip, and then we try to find out a mathematical part and now design a chip. Right? So if I convert this filter into a mathematical representation, this is what it is, right? X1 is a P1, P2 till Pm, and weight matrix, the convolution filter layer, weight 1, weight 2, weight 3. So the 1 is bias that we usually include, and then we sum it up and we'll get the output of the filter. And this is how we represent it mathematically, which is actually, this is the line equation. If you actually see, it is y is equal to mx plus c. So that is how in the other aspect. And when we actually come up with the weights, and when we translate this idea to architecture point of view or the execution point of view, it is actually fetch and multiply, because the value comes from the input, and then we multiply with weights, and we add and we'll store. And yeah. So this has been realized with this compute unit, where we get the data from the memory, put it in the registers, and then we do the arithmetic, and then we write it back, right? Okay, if I put all of those things in the same slide, so we have the filters ready, convolution filters ready, and then this is the process, and then we try to map it with the hardware architecture, right? Okay. This is where it gets somewhat complex. When you actually look at the neural network and then try to identify the patterns that how it executes, this is how it looks like. You have multiple entry, multiple exits, correct? See? And it generates lot more intermediate data than the input data. Sometimes it's more than the weights that's been utilized. That's a precise idea that I'm trying of this slide. So it generates a lot more intermediate data than the input and the weights. So we require a large chip, and NVIDIA has actually succeeded in providing all of those GPUs. NVIDIA, AMD, Intel, and a company, right? And there is no definite structure for this inferencing. I can actually remove this node. In the previous presentation, IBM has mentioned about pruning, compression, sparsity and stuff like that. We can apply the same techniques, right? And then try to remove some of the nodes. Then this structure becomes really complex. We do not know when to schedule, how to schedule, correct? And that's the decision making of when to schedule, how to schedule, and where do I keep this intermediate data is actually a tedious job. It is maintained as non-AI workload. It is actually not AI workload, it's a non-AI workload. So this is where this load and store architecture coming in, and this is the CPU and GPU. So now we have the picture of inference, how it works. Can we actually use the CPU or existing GPU to find out where we can execute it more efficiently or sustainably? Okay, so GPU has a lot of units, compute units, and we can run so many things in parallel, and CPU has some intensive logic as well we can run. But the point here is the entry and exit. So for this so much big room, we have only one entry. So imagine if you have entries in other sites, so there is a frequent data flow, people flow, no more obstructions and stuff like that, right? That's precisely is what hurting, correct? So basically, when you try to have the workload with the hardware architecture, and this is the standard picture, that's arithmetic intensity is nothing but how many flops that you take, how many bytes you take inside the chip, and how many operations that you can do with the fetched in data. That's arithmetic intensity, and the attainable flops, because you cannot, sometimes you will be having more intensive work here, but all other execution units remain idle. So basically we may not be able to attain the peak flops that they talk about. Okay, so ideally if you take this square as 1, whatever minimal value that we can achieve is what the efficiency, correct? If I can achieve only this much of attainable flops, then I'm wasting 40%. I'm paying for the cooling power and stuff which I'm not utilizing it. Like some of us have high-end phones, but they use it only for talking. Okay, so there's slightly more details to it. When you actually look at this picture, there is a non-linearity coming in. Correct? Why there is a non-linearity coming in? Because when you have ones and twos and threes, it is fine. You have slight, curves. When you have slight curves, you can actually represent it with two or three more lines. One line this, one line that, and one line this, right? So you can actually have a linear way of, modeling the inputs. But when you have fashion eminence, right? Fashion eminence have patterns like you see a word on the shirt, right? How do we predict that it is a shirt if there is a word on it, right? Because it gives you a lot more finer details that it may not be a shirt, right? So that's where the non-linearity comes in. And this is how the points, if you plot these points on the 2D, and if you want to separate these points, so we need a curve like this, right? To separate these points. I cannot actually do a straight line and cut it. And that's where this non-linearity come in, right? Non-linearity is something like higher order terms like square, cube, or if it is sine, if it is a repetitive function, it is sine, cos, stuff. Right? Okay. Are all these same? Are all these pictures same, represent the same object? Yes? How many of you say yes? Good. Thank you. So how do we teach the neural network? How do we teach the neural network to say all these things are same? Okay. Now let's see the AI workload operations, right? Basically, these are all matrix operations and transformation. Transformation is both, it's a lot of operation. You can either shrink it or expand it, or you can move the object from one area to the other area in the image, or you can stretch it in one direction in a parallelogram ways. All these are matrix representations. You can represent the matrix with that, right? As I compared the nature and the senses in the first slide, the same matrix can be used, operations can be used as a convolution filters or as a transformation. It's all one and the same. So mathematics is so beautiful that you will definitely enjoy reading and experiencing a lot of it. And I'm truly a mathematical intensive person. Wanted to be. Let's see. And the second one is the statistics and probability, right? So you know that it is you are actually feeding in the statistics point of view through the data set to the neural network, and want neural network to predict. That's the probability comes in, and all these things are guided by the probability, the dense layer that makes the decision, right? And that is where you see the softmax function that's coming in, right? You will see a different confidence score for all these three things, right? And when you see a different confidence score, you will try to guide the process, the neural network, in such a way that no, all these three things are same. So try to predict it in the same way, and that is where the last few layers of the neural network makes that decision, right? Because you're teaching a lot of probability point of view, the statistical higher order features point of view in the last few layers. So the dense layer makes an important. Basically, it is a signal processing. If you order the neural network, the pixels, and if you try to find out if you plot the values in a x direction, in x and y axis, the y axis has the intensity of the value, it actually draws as a signal. So when it is the digital signal processing that we are doing it, but under the different name in AI. And that is where we are trying to discover a lot more features, and then we do a pattern grouping. So this is actually the pattern grouping. What we have done here is the pattern grouping. So I have this red slice, green slice, but green slice is transformed this way, but the green slices appears this way. So we're trying to give more pattern grouping and then make the decision, right? So the mathematics across all the domains, it's been utilized in the neural network. It is not just one operations. It is not just one multiplication. It is not just the matrix multiplication alone. So it has statistics point of view, probability point of view, and signal processing and all of those, right? Now let's see the characteristics, right? With respect to the generic, I mean load store is a generic business application and AI application. So with respect to the control flow, you have more go-to statement, if-else statement, for-each statement, and all of those things, right? So the control flow is really complex in the business applications, right? But with respect to AI, it is all feed forward. You just keep going. There is no way of going back to the layer one and do something, right? And it is simpler. Flow is simpler. Data access is sequential or aligned. So when you actually fetch the program, your program and data, when it is fetched inside the CPU or GPU, it actually gets the instructions of the data and the instruction for the next consecutive executions, right? So it is all aligned, basically. But in AI, it is totally parallel and unaligned. I'll focus on unaligned later. With respect to power, it is low relative to AI because that's what I said. The server comes with 1 kilowatt hour. It came with 1 kilowatt hour, but not now. It's on the other side. And it is high due to parallelism because we wanted to execute a lot more parameters. And that is where we see the power goes high. Data formats, integer or float. And AI is sub-precision FP16 and FP8. I'll try to give an analogy, stop here and give an analogy on data format because it's the most discussed format or type or term in AI, right? Okay, let me. So what is integer and what is float and what is this FP16 and FP8? Let's say you are discussing with your professor in the classroom. And especially the professor teaches electromagnetic field theory. This is one of the most complex subjects according to me. Okay, and if you ask a question, what does the professor say? The professor can give you the answer directly. Okay, this is the answer. Or he can also guide us to refer a book. Okay, refer a book. When he says refer a book, it's a simple statement which has, we have to go and find out where the book is and all of those things, right? But if he adds, the professor says that go to the library in XYZ building and go to this floor, third floor or fourth floor, go to third or fourth shelf and get into this rack. The second rack, fifth book, and 100th page, second paragraph, third line. So when he uses integer format in his expression, right, he could actually say that go to the XYZ building and the library, right? There may be 2-3 libraries, right? So he has to stop there, and it is for us to find out that which rack, which shelf, which rack, which book, which page, right? Because the distance that he has covered using the integer, right? Let's say in the first instance, I can say it is 1 kilometer and in this specific direction, and in 30 meters in the other direction, and 100 centimeters in the other direction, and say 10 millimeter, because you are getting to the exact line of the page where we have this reference, right? And that if the professor uses integer, he has to stop it at the library level. If he uses FP32, then he can actually represent the distances, right? The distance between the classroom and the library and the book and stuff, because that's the exponent part of it, because exponent part of it covers the large distance, and the mantissa part of it covers the precision. Which library, which book, which page, which page, which book and which page and which para, correct? And so that, so if you, in case the same discussion happens within the library, and he does not have to mention about go to the XYZ building, because all those information is already, that's what the context aware that is coming in, right? So in that discussion, he might have pointed out to a specific book, or he myself, take the book and read this para or read this book. And that is where this precision coming in. You can reduce the mantissa part of it, the distance of the information that you are trying to process, and then give more precision. Because I don't need, for FP8, I don't need significant exponent, because I am already discussing within the library. And that is what a data set. And if we know, how do we, if we know more about the data set, we are likely to choose a better data format. And the techniques like model pruning, model compression, and all of those things can do a job to a certain extent. Because most of the things that we do, it is during the conception of AI model. How do we want to build? So that understanding is much more needed than applying those different techniques. Those techniques are really important, and we need it, because if the data set is going to be like 15 trillion tokens and all of those, it is highly impossible for us to get into all of those. At that time frame, yeah, we have to use those techniques and find it out. But we need to really get into that so that we can build an optimized, sustainable chip that consumes less power, which does not require any cooling. That's what I'm coming to. And computation is arithmetic and intensive operations. Okay. What is the impact on hardware, right? So as we talked about different data formats and things like that, that actually gives us irregular memory access. All the requests that we generate, it's going to be irregular, because you will have integer coming in, you will have floating point coming in. We cannot access all of those at the same point. But when you do a subsequent access to those kind of data, we will have irregular memory patterns, and the memory patterns is costly, as you have seen in the previous presentation, right? Whatever memory access that we do, it is the costliest. And we require a lot of compute units, and fortunately the weights and biases are going to be the same if you are doing the inference part of it, right? Because we are not going to change any weights. We just use those weights for inferencing. And then more intermediate data requires high bandwidth interconnects, because high bandwidth is like similar to opening these doors for this room. But that might create some kind of noise that we need to take care of it. But if it is applicable to our use case, we can open these doors as well. So basically, for accelerators, we need to have a efficient memory access, and that is where we can save a lot of power and time. And the computation needs to be accelerated, and managing the intermediate data is the most research area now. It's a hot topic in compute memory, PIM and all of those things, right? And all those things are pipelines, iterative processing pipelines, because the neural networks are staged as pipelines, as you've seen it in all the diagrams, and it needs to be scalable to volume data. So with respect to the principles, we need to have a memory, but it should not have a longer fetch cycles. We need to have compute that can be realized using systolic arrays. We can actually store weights in on chip, and we can actually come up with pipelines that reduce the data movement and scalable interconnect, right? So we have started from what is AI and dimensionality, patterns and prediction. How did we actually convert coming into designing the chip, right? So we have discussed about architectures and the principles now, and that is where the feasibility part of it is what I'm trying to arrive here with this slide. So we know, we have seen it in the previous slide, it's what knowledge, guidance and AI model, right? So what is actually the training and inference? I'll again go back to my analogy on the college side. So let's say how many of us have given the intern, what do you call, forgot, the intermediate exams, right? Assignments and stuff, correct? And some kind of semester exams, right? And once you have those internal exams than the public exams, right? The professors or the college teachers would try to give more feedback to us, saying that you have made you have answered these questions in this way, so you have to actually do this way, and they give some correcting patterns and all of those things, right? With respect to the final exam, they have the key to correct your paper. They'll just check whether the key is there and your test paper is matching to the key, and then they'll just put a tick, correct? So this is what the neural network training is ideally, and this is what inference is, because we need lot more data to correct the guidance, right? So from the feasibility point of view, this is again the neural network trying to train. This is a training view of a neural network basically, and you have the input data, and this is a feed forward network. You need to actually save the actual values and the target values. Basically, once you have the papers corrected, you have the papers to be reviewed with your professor. That's the actual value that you have got it right now in the examination. And the target value, let's say you have got 80 out of 100, and the target is 100 out of 100. So professor or the teacher would give us, evaluate, and based on this loss function, they try to correct the value. They give you feedback, correct? And that feedback goes back to the neural network to us with the adjusted weights and bias. You should have answered this way, you should have answered that way, some kind of slight corrections here and there till we achieve 100%. Right? And in the inference stage, because you are appearing for the final exam and you have learned many things through the guidance, and you don't need all of these values. Target values, you don't need to have adjusted weights and biases, because you keep saving that information during your exam preparation. You keep saving your teachers or the professors' feedback in written or in some form of the other way, right? You keep that and refer. But when you go to the exam, you'll have only the pen and the model, correct? And you don't need all of those things. What happens next? Suddenly, you need only 1/4 of the hardware. GPU is very useful in AI training, absolutely very, very useful. Otherwise, we would have not come to this stage in AI. But do we really use all of those during inference? That's the second question that we are trying to answer, right? So we have come from feasibility and trying to address sustainability, because I do not want to employ something which I do not use, because it's a waste. And this slide you might have seen previously in the previous session, that this is actually the paper from Stanford, and the relative cost is 6,400 x. That's the energy relative cost. So we, by all means, we try to save some kind of memory access. The first time we try to save by identifying the right set of formats, whether I wanted to use integer, whether I wanted to use floating point, or sub-precision floating point like FP8, FP6, and something like that, right? And that's the first decision we make with respect to the architecture, because all our memory consumption is with respect to, all the power consumption is with respect to the memory. Okay. This is another aspect of sustainability. These are all different tasks, the AI tasks, but our focus is on the image classification side. Okay, this side, image classification side. If you look at the text classification, is 3 times less costlier than the image classification. Text has naturally some kind of intuitiveness. If I say a word, dog or cat or mountain, each one of us will get some kind of mental picture in our mind. How does this cat look like? How does this mountain look like? And all of those things. And none of them is going to match between our understanding. So language processing, fundamentally the LLMs and stuff like that, operates on a lower dimensional than the image. I'm not sure whether LLM guys are here. Okay. So image is always a high dimensional data point, and if you combine it with video, it's going to be more complex. Correct? And the energy parity that I'm talking about is, you train this neural network probably 1,00,000 times or million times. Correct? When you want to build the neural network with all of this actual target values, weights and stuff like that, probably 1,00,000 times or 1,000,000 times. But when you do an inference, we go in the orders of billion, 63 billion times. The number that I've arrived, because we also take care of the CCTV surveillance, people detection, counting, tracking, and all of those things. So if you take one camera that actually runs at 20 frames per second, right, tries to detect whether there is a cat entered or not, actually runs the inference 63 billion times in a year per camera. So in Zoho, we have more than 3,500 cameras. It's one of the, in the largest campus, around 10,000 people, we feed around 35,000 meals per day. And we monitor lunch halls using this technique. Whether that lunch, we have multiple lunch halls, around 10 lunch halls, and employees can find out whether the lunch hall is free or not. Correct? So basically, we use these kind of techniques to find out, and the inference time is actually per camera it is 63 billion times, and we spend a lot of power. But fortunately, Zoho has taken a practice that we bought a lot of lands and put a solar power. Again, that comes to a question: who is going to provide air and water, right? So the energy parity is not the same. So buying GPUs for training, most of the people have deployed it for inference, which is again a lot of waste from the perspective. And then what happens is we spend a lot of energy in power and energy in cooling and stuff, right? So, and still we cannot use the hardware with the full resources. It's a partial use of hardware. Correct? Okay, now coming to the viability point of view, this is where I talk about this open source flow. I'm not really sure whether you can read the slide set, but basically this one is the front end part of it, okay, and this one is the physical design part of it, and this one is the physical verification part of it. This is out there, so out there in internet you can find a lot of references, so there is no need to take notes. basically we can do synthesis, STA and DFT, and do this pore planning and placement, clock tree optimization and global routing and stuff like that. And then we can actually do the physical verification. So basically this is a front end. The back end is divided into two, physical design and physical verification. And so basically this is the same the same open lane framework, but it is with more details. So you can actually sign up with timings and all of this. So all these are open source tools. You can go to home today, do a git clone and run it. You can do the same inference chip in your desktop. Okay, no licenses, but there are some challenges. You are welcome to approach me for setting up that flow for you. I am ready to collaborate, work on because it's an open source. Okay, now we are coming into the design part of it. So when we train the neural network model, we use this Python language, and this is actually the TensorFlow code. And if you actually read the code, it is like layers and layers, which is inherently it is a pipeline stages. The data is moving from one layer to the other layer, another layer to another layer. That is what? It's a sequential pipeline, correct? And when that's a Python code, and we wanted to translate it to a C++ code because we wanted to get into RTL. Only when we get into RTL, we can synthesize. After we synthesize, we can do the PDK, and PD flow, right? And this is the C++ code. You are welcome to use ChatGPT to generate this code. Okay, and yeah, we can actually do the whole flow, and using the llama, Meta's llama. We have tried a couple of experiments, and that is actually more and more encouraging. And that's what I'm really scared of. I'm thinking of always this $30K per year, 900 million tokens. That is actually scarce. We can actually come up with new algorithms and new simulations and stuff, and we can find out more and more, efficient designs. But the design that I'm talking about, this design is not efficient. I will also tell you why it is not efficient in an aspect. And this is how so basically the C code is being converted into RTL through you can use Xilinx flow for, or scale HLS to convert this into a RTL. But we need to spend some time on this custom floating point operator, because this has been designed for floating point 16. And that floating point 16 is based on this small block, multiplier block. Okay, so because it's an open SDK, open PDK from the Skywater, and there are a lot of other open PDKs as well you can try out. So in order to build this, multiplier is the challenge that we have to build. And this is a 14.16. And in case of pruning and compression, what happens is we can actually build a neural network with multiple precisions. So because in some cases what's happening is, when you try to reduce the floating point 32 to an integer, and then FP8 and stuff like that, the intermediate layers sometimes requires lot more representation. For example, let's say woman's handbag. If I say woman's handbag, there are plenty of designs. I don't think we can actually put it in a specific representation. But I'll have only, in my shop I have only 15 varieties. Right? That 15 varieties, but some varieties I have really intricate designs on the hand side, or the colors also. I cannot represent the color. I cannot say that, okay, it is a violet or green or red or blue. There is Irish, greenish and blue, something is there, right? How do I represent this complex pattern, right? And I want to represent, I have only 15 bags with me, but I wanted to represent all of those things. So that makes the formats more sparse. And I need intermediate number representations in such a way that it actually helps us to make the decision correctly. So what happens is in the internal layers, when they try to convert the input into integer 8, and then they do process on integer 8, and when they come to a decision making layer, they'll have to convert this integer into floating point. So most of the conversions, pruning, compression methods are not as good as we think. We'll have to put a lot more effort in make things happen. And when we do the intermediate conversion, that has high penalty on the hardware. But with respect to this kind of designs when we make, we can actually bring in those intermediate changes in a custom cell, as a custom cell. And the FSM is very, very, with minimal number of states, so you do not have any complexity in meeting the timings. And this is with respect to viability. This slide from eFabless is one of the companies, this is one of the companies who actually help us make chip designs with $10K, right? And they actually provide this SOC template. Whatever the inference that we are going to design and put it in synthesis, and then add the GDS2 here or here or here or here, and then we can send it to them. They'll manufacture it and give it to us. It is not just one company, there are many other companies, but this reference is from eFabless. Right? So in order to actually get, configure the template, so we need, they call it as a wishbone bus. So we can actually connect logic analyzer, GPIO, analog IO, and interrupts and all of those things. We need to make sure it connects, the external world is connected to our inference chip. And these are all the things that we need to decide. It's a reset, clock, power, IO and RAM. These are all pretty basics, right? There's nothing complex here. And these are all the signals that we can map. And there are control signals, status signals, memory signals, and GPIO signals. The control signals are helping us to manage the execution of the model. So how do you interface the software to this inference chip? Right? You need some kind of control mechanism. That control mechanism is going to be really simple, because you are going to start or end, reset or clock, right? And the status signals is idle, or when the data computation is ready, we can actually, it gives us the status, and then we can observe it in the software and then observe it. So these are all the design methods. With respect to the design methodology, these are all the bits that we A and B are inputs for the multiplier, and this is with respect to the multiplier. So these are all kind of data sheets which I am trying to skip. And this is a configuration file that you need to actually give it to the open flow, the open source flow. And you can actually say that these are all the optimization settings that you can do. Here the clock is 100 ns, the 10 megahertz design. And the buffer size, the maximum buffer insertion is around 75%, something of that sort. And we actually let the tool to liberally use all the resources that are available in the open PDK, so that it can design and route and give it to us, right? And this is the floor plan and routing constraints. Basically, it has the threshold is, antenna threshold is 110, and we actually use the heuristics model for antenna corrections when we, it is actually not the antenna corrections that we do here. And these are all the metal thickness or the routing offset and all of those things we mentioned. And the target density is 35%. So we expect the design to occupy 35% of the user space area. Okay, and these are all the power nets. And these are all the, when you use this kind of cells, what could be the clock period internally and stuff. Okay, this is the viability point of view. So we wanted to, for these kind of chips, because it's a resource from the capital point of view as well as from the power point of view, we need to have a maximum yield. So in order to get a maximum yield, we need to get into the mature process, right? Rather than working on 9 nanometer, 10 nanometer, or even 45 nanometer projects. So this is on the 130 nanometer PDK, where we can get actually the maximum yield. And when we run it on the low frequency, which is good enough, this 10 megahertz design is actually the good enough frequency for doing the inference, given this design. So we'll have minimal signal integrity issues. And it is routable, and it meets the timing, and it is completely synthesizable, and we can actually integrate into the system. So synthesis is, these are all from the synthesis report. So the complex cells is very less. So this is if you see this, the buffer has been used a lot than the other design. So this design has a lot of scope for optimizing it. That's what the synthesis report tells us. And this is after the detailed routing. It actually gives a lot more data. And when you look at the post layout, timing analysis, you have still 18 milliseconds to catch up. That means you can include more and more logic as well now, right? Because we gave it liberally the constraints, and then get the design out. The power. So there is okay. If I compare this power 1 to milliwatt, that means I can use this chip for image classification with respect to that MNIST with the mobile power bank for a week. So that's the comparison. And that's a GDS2 flow which came on my desktop. So from the challenges point of view, this particular design has a long route. So actually that one violation, takes a lot of time and a lot of memory. So we need a 28 GB RAM desktop to get that running, and clearing antenna violations is actually a challenge. And here we have given the relaxed timing, and it is actually not DFT friendly as of now. We need to include few more DFT signals inside it so that we can get the maximum yield, right? Maximum ROI. So the references are from eFabless, TensorFlow, YTSHLS, OpenLane, OpenRoad. So with respect to the affordability, mature process is a good one, is good enough to go for it. And we can, since we are using the open source, we can actually get a lot more IP blocks from the community. There is a marketplace for this. We can get it from the marketplace, and we can have a manufacturing partnership, right, with multiple vendors, because it's an open SDK. You have the choice of going to vendor 1 to vendor 2 and vendor 3, because it's all open PDKs, right? And EDA cost is almost zero, but we need proprietary EDA tools to get this design really optimized to the last mile core. My gut feeling is we can actually reduce the power consumption to 15 milliwatt, but whether the design works or not, whether our approach works or not, and all of those things can be done using the open source, right? So prototyping can be done in 10K, and basically the scalability. So as you've seen it in the first 3 slides, right? The first 3 slides, I have talked about the MNIST integers, as well as the fashion MNIST, as well as this elephant deduction, face deduction, and all of those. all those come under a same neural network board. Okay, so you can have the same layout with only the values, weight values programmed differently within the drum. Correct? So, same synthesizable architecture, and if there is a change in drum, you obviously have to do some kind of change in layout. But the most of the work can be retained for 3 different chips. So we can make 3 different chips using the same flow, because we do lot more inference than the training. So it is good to invest on this kind of technology and make a application specific inference chip. So multiple precisions with the multiple precision pipeline with the multiplier macros, that's what I meant. When there is an intermediate conversions, we can actually avoid those by building the better multiplier macros, and it actually complements the software. The software development is very minimal for these kind of chips, because most of the things are done by the chip itself. And the key takeaways are, from the cost perspective, we can go on a mature process and the open source EDA, and we can actually follow the standards. From the resource constraint, power and cooling is not required for most of the stuff, and synthesizing neural network as is the benefit, right? So we have to take some kind of high level decisions, but we can completely synthesize the neural network as is. And we have the configurable management SoC like FPGA. We can actually make the same chip. Instead of ROM, if we can make it as a RAM, and if there is a way to upload the weights at the beginning of inference, then your chip can work for multiple inferences. So that's what I meant by configurable via management SoC. So thank you. That's all I have.
Thank you, Raja, for an engaging talk.
Yeah,
so we can take question and answers now. Can we have the mic? Any questions from the room?
While training the models, have you experienced any hallucinations regarding LLMs as well?
Hallucinations in
LLMs?
Obviously there are.
Yeah. Can you shed some light upon that as well? What sort of...
what are the ways that we can reduce hallucinations?
And at the same time, how you overcome as such those hallucinations?
So hallucination is inevitable, because all the things that has been learned is only through the probability and statistics. It can actually tell us how much the neural network is right or wrong about a certain things. That's what the confidence score comes in. So we cannot have a probability with 1.0, correct? Because it's not certain. So hallucination is going to be there. With respect to how do we avoid the hallucination with respect to your own domain, that we'll have to take it a modular way. So that has also been discussed in a couple of our talks in the same forum. Basically, you have to take it as a modular way. In order to design the OS using the LLM, you have to come up the top-down approach as well as the bottom-up approach. Top-down approach is how do you actually divide your operating system in terms of memory, in terms of drivers, in terms of IOs and stuff like that. So that's a top-down approach. Then at the bottom-up approach, you will have to say, okay, give me a memory function, generate me a function that can manage memory when there is a request for allocation. So these kind of things you'll have to write a prompt in such a way that it goes in top-down approach and the bottom-up approach, and somewhere we humans need to marry these overflow.
So combining both of these top-down and
Correct.
bottom-up.
So that has helped us in this case as well.
Thank you so much.
Yeah, thank you.
Any other question in the room? Yeah.
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 How? Yeah, this is image classification with respect to all the weights that we talked about is all from the MNIST flow. This flow it works only for that MNIST kind of scenarios because all the filters that it processes only one filter. It is not RGB filter. It is not three filters. Three that can actually get the patterns out of red, green, and blue colors. So this works only on the gray images. Okay, that's what I covered in the first flow. You have the Python, and then we can generate. You can feed that Python into a ChatGPT kind of tool and get the C++ out. And then once you have the C++, then you can actually feed it in the HLS flow. And the HLS Verilog is actually not readable. When it generates the Verilog, it is not readable so it has only according to me, it has only the always block, or otherwise it looks like a netlist. So that's why I didn't show that here. So that's the flow. You have the function and Python function to C++, C++ to HLS flow dumps out RTL goes to the synthesis. The inference chip. The inference part is completely on this chip, and then that IP you can actually put it in the frame by the eFabless or some other company, and they will manufacture it and then package it and put it on the PCB, and they give it to us. No, come again. Yeah, you are welcome to say that, yeah. But there is a lot of human intervention. Yeah, you are welcome to say, yeah. Yeah, probably we can take it offline. Sure, I'll talk.
Yeah, hello. Yeah, so my question is regarding the power estimation.
Okay.
So how, if provided I have an HLS tool, like I have my neural network in the HLS, but now I want to estimate the power, not just the static and dynamic, but given a particular number of layers and particular application, I want to know how much power it will actually require. For like 3 layers or 5 layer, it will be different, like. So how do we estimate that power? Are there any open source tools, or even if it's like Xilinx one provided? So not
Okay.
the vectorless, but actually
From the
based
HLS
upon,
point of view?
HLS or yeah.
So from the HLS point of view, you can actually simulate it and see whether we can achieve some power numbers. Or else we can actually do it in the CPU. We can actually have the okay, so HLS means it's a C file, right? If I can assume C file. Then if you run it as a C file or a C executable in the PC, so we will get some kind of reference power number. So from that, we can try to synthesize using scale HLS or some other HLS tool, and then we can simulate that part alone also, because this PDK also has the power numbers. So how many cells that we use, whether it is routable, then we can actually substitute that and then come up with it.
Yes, so for example, my design is I'm using Xilinx HLS one, and then after the complete implementation and all synthesis, so it gives us that based upon the number of LUTs and number of these,
Correct.
like it gives us.
Correct.
But what I want is that if I run for example, I have a neural network which is of 6 layers. I run it, so it will have some time and also their data flow, like their
Correct.
data in and out.
Correct.
So I want that how much power it should, power estimation for like running that particular neural network,
Okay.
not just the vectorless one, where it's only dependent upon the number of LUTs and number of flip-flops.
Okay, good question. So for this kind of chip, most of the gates are actually at the active state, because it is a pipeline processing. When the data moves from one pipeline to the other pipeline, the new data comes in. So it is a maximum utilized chip. So when you have the static calculation of the power is actually very similar to the dynamic power. Maybe here or there somewhat it is less, but the static calculation is good enough. That's what I said. Okay, we can have this chip can execute with the mobile power bank for 5 to 7 days for this task.
Yes. So, but for example, if we have like a clock gating system, so there, if we get like, for
Yeah,
example,
so it doesn't require clock gating because it is always on, because you are moving the data from one pipeline to the other pipeline continuously for a year. So you have 20 frames per second that has been fed to this chip. So there is no way that you can switch off, and that is why the CTS is not much here. Okay, and there is no need for power gating because we wanted to really save the power. Basically, the clock gating and power gating comes when the particular part of the chip is going to unutilized for a specific period of time in the application, right? But here we are going to use the full chip as is.
yeah, but so we are not utilizing the sparsity. Like for example, after the ReLU, we will have more of the zeros. So if I want like, okay, if I have a 0 as an input, I will not use the multiplier and directly give 0
Correct.
as an output. So
Correct.
we can, that way we cannot explore it.
Yes.
Okay.
Thank you.
Thanks.
Yeah, thank you.
So, Raja, on behalf of the organizing committee, we would like to felicitate you with a small token of representation.
Thank you. Thank you.
We will start the next session at sharp 2 p.m. So please be in the room by 1:55.